Yakov Varshavsky from Lusztig. Finiteness properties of affine Springer sheaves and elastic projections.
Okay, so thank you very much to the organizers for inviting me. Okay, so let's first give some plan what I'm going to talk about. One, it will be motivation, maybe zero. Zero in the sense that because it will be independent of interest, but just it will illustrate why I'm interested in this kind of equation, what kind of general picture is behind. And maybe I want to say, I will talk about Lusztig result in conjecture. Second, I will say that Lusztig theorem in the particular case of the GLN over Q. Second will be main result, which is the same as Lusztig conjecture. For GLNF. Okay. And later I will say the somehow main ingredients of the proof. The proof will be in something combination of the Lusztig results plus some finiteness results. And I will divide it into two. Finiteness results for regular semi-simple affine Springer fibers. And the last one, I don't know you'll have time, but the same for affine Springer sheaf. And if I don't have time, somehow the difference between these two, that here is not a regular semi-simple locus is taken into account. It's maybe relates to Ben's question to the Alexis. Somehow we don't know how to do the perversity structure, but some finiteness results we can do not only on the regular semi-simple locus, but also. Okay, good. And everything is joined with Roman Bezrukavnikov and David Kazdan. I might say that somehow there is a related results about perverse sheaves, etc., but it will be somehow it's connected, but not really appear here. Okay, good. So let's start. So motivation. Motivation is the following. So let G be connected reductive group over frequent fields. I will not identify with C. And then let us say V will be the group of i's. Maybe that's important. L will be prime, which is not divided Q. So, and we consider somehow all the representation, etc., will be over Q bar. So we will consider representations of Q bar. And of course, if you start the representation, there is a natural vector space, which is V, which is the vector space of class functions. Of course, one of the first results in representation theory of finite groups says that this vector space has a natural basis. B consisting of traces of irreducible representations. Yes, and by the way, when I say irreducible representation on GF of Q. So this, of course, very standard. And now the important up, down. Okay, and the result of the theorem of Lusztig. Oh, actually, the series of works of Lusztig says that actually consists of two parts. One part says that actually V has another natural basis. Let's say write B prime, which is collection of kappa prime where rho is again irreducible. Namely, the basis is different, but the parameterizing set is the same, such that this is what is called so-called almost characters. In a second, I will say what it is. And there is the first part and second part. If you have a two bases parameterized the same set, of course, there is a natural question how to pass from one to the another. And the theorem of Lusztig says that actually B and B prime are connected by non-commutative Fourier transform. Fourier transform. For example, so what does it mean? This means that of course, in particular, of course, it means that somehow every almost character is a linear combination, is explicit linear combination of character and vice versa. For example, in some cases, but I'm saying this because this I will be talking about. But not always. Sometimes it's some explicit linear combination. Good. Maybe I want to say a couple of words. What do I mean by almost character? So people are higher than Israel, but in Israel I don't have to write it that low. Okay, yes. Somehow what I want to say, maybe I want to say more precisely, almost character. Or say more precisely. Lusztig defines the following thing. We have a derived category of G covariant L-adic sheaves. These guys there is a certain perverse sheaves. G covariant, and Lusztig defined here character sheaves. Sheaves and almost characters, and every, let us say this, it is I will write in the following form. It is something like F rho, where F rho is the character sheaf, and this guy is what is called trace of Frobenius of rho, namely the functions which corresponds to this sheaf by the Grothendieck sheaf functions correspondence, or in less precisely coming from geometry. Good. So this is what happens over finite fields. Now what happens, and I will be less precise. Somehow this might be A. B. Now let F be periodic field, but periodic field I will actually you can do everything in the mixed characteristic case as well, but I will only use the equal characteristic because geometry is more clear what I mean by this. So it is this, and G will be the same thing. Let us say unramified, connected reductive group of F. Unramified means splitting over unramified extensions. For example, you can assume split if you don't care. In this case, Lusztig conjectured that let's say the picture of A, let's say, can be extended to G of F, to G whatever of F. What do I mean by this? Okay, first of all, you have to replace this guy. What is this guy? This guy, instead of V, we can associate the invariant distributions. G of F. But actually, it's okay. This is probably what you want, but Lusztig does this. Lusztig, instead of consider all invariant distributions, he only considered actually on the compact locus. So the picture is not complete. It's only extended to the compact locus. In principle, we probably would like to do, but there is some, first of all, Lusztig doesn't do it. And also there are some reasons why maybe it's not possible. Okay, also then we have, of course, we can talk about irreducible representations. Then we can, this will be V tilde. So let's say V tilde is spanned by the character of irreducible representations to restricted to the compact lattice. Namely, if you don't restrict to the compact locus, then it's roughly speaking a topological basis. But if you restrict, it's definitely not a basis, but it's definitely. And also, Lusztig suggested that there should be exist the almost character plus Fourier transform plus that beta and beta prime are connected by non-commutative Fourier transform.
What kind of representations do you consider here?
Smooth representations.
But he says anything concrete only in step 0 case.
What?
He only says anything.
Yes, you're right. You're right. You're absolutely right. He only says it for the. You're right. Lusztig does it, of course, for the depth 0. I'm sorry. Thank you. Okay. Depth 0 actually unipotent. Namely, formally speaking, Lusztig speaks about unipotent. It's most likely it's possible to. It's not very difficult to extend to depth 0, but it was not done. But beyond this of course, it's never done. Thank you. Yes, and representation. I mean, there's the smooth representation, namely. And in particular, the topology of QL bar with it's you can identify it with C. So far. Good. And now what I want, sorry. No, it's because I'm otherwise.
What does depth 0 mean?
Depth 0 means there is an invariant with respect to first congress. Which is somewhat looks like yes, but I will formulate when the process result. But thank you. For example, somehow in the main result will take care of representation with consider Ivachori invariant fixed, and depth 0 are a little bit more general. Good. Sorry. Okay. Yes. Now you can ask. Yes, as I say, somehow our result we will actually establish particular case of this conjecture in the case of Gilda. Now you can ask, let us say, why I can. There are two answers. First answer, it's nice to have there are two answers. Answer one is it's nice to have two different descriptions of the same object. If you can take explicit representations, if it's coming from geometry, usually it's interesting. So two different description. But actually, the second answer, which I really interested in, because that I understand that actually, let's say conjecturally, Lusztig conjecture implies conjecture implies Langland's conjecture. By this I mean as follows. No, local Langland's conjecture. Langland's conjecture says the following: that if you think somehow there is a, he says something very similar, but in different terms. He says the following: that if you have the space of all invariant distributions, first, First of all, it has a basis, a topological basis by irreducible representations. And also, there is another basis. Basis which contains, of course, of linear combination of this, consisting of endoscopic distributions of generalized functions. And to those who don't know what endoscopic means, but endoscopic is, for example, stable. It means so invariant distribution is, roughly speaking, functions which is invariant under the conjugation. But a stable one, which is invariant with respect to conjugation by the G of the F bar, of the F bar. In particular, stable distribution has much better algebra geometric properties, which allows, for example, to pass from distribution from one group to another, and has many important properties. For example, like, okay. And now you can ask, what is the connection? You can ask, okay, there is some similarity, of course. So here the Langland says that it has there is a space of invariant distribution has two bases, and Lusztig says that it has two bases. And you can ask, what is the connection, and why there's something to do with this. And now, okay, now what I claim is as follows. So in particular, this means that, for example, some explicit linear combination of characters are endoscopic. And now what I want to say is a relation, but now, first of all, there is exercise that actually Langland's linear combination. It is a linear combination of Lusztig linear combination. Linear combinations. Okay, maybe just without writing, somehow if it have depth zero, there are two elements, S and U. And Langland's linear combination is a Fourier transform where both U and S and U are taken into account, and Lusztig linear combination that U is fixed and only S is taken into account. So this is just this. Now, if you have a Lusztig conjecture, if you assume Lusztig conjecture, so it is linear combination of almost characters. And now what I claim is that somehow, and now there is this conjecture, then this guy is endoscopic.
Each almost character is endoscopic.
What? Yes, each almost character is endoscopic. And moreover, what I claim is that the almost character which appears in linear combination actually belongs to the same endoscopic piece. And moreover, this is known in some cases. Known in some cases, and the main ingredient is theorem of U. So using this theorem of U plus some geometric assertion, using theorem of U, you actually this is somehow we don't know in some cases. So in particular, besides of that it is interesting by its own, Lusztig conjecture, for me at least, motivation is that it's nice to connect something which at least before I understood it, namely before Kazan explained it to me, I didn't know that these conjectures are actually related.
So for GLN, I assume almost characters and this first space are the same. And what's this line one spaces?
It's the same. Everything is stable.
Everything's the same.
Everything is stable. For the GLN, Langland's conjecture is empty. I mean, okay, in this, let's say, Langland's endoscopic conjecture is empty because everything is stable. Okay, good. Let's now start the real thing. One thing I forgot. When did the start?
Fast.
What? Fast. Good. Thanks. Okay. Now let's start this. Now I say that those who somehow who are lost can forget everything because we're starting completely new topic. So let G. Okay. Let G be connected reductive group Q. For example, later we will G equal GLN. To those who know it's fine because this is actually the main somehow case where actual result will be. Okay. BG Borel. Now what we let V be irreducible representation of G of Q such that it has a B invariant vector, meaning B of Q vector. Then, of course, B of Q, this guy, it is irreducible representation of the Yakov algebra. So finite Yakov algebra. Just functions of G of Q, which is B invariant with respect to this guy. And now I claim that actually this algebra is actually the same thing. It is just irreducible representation of the binomial. Because this algebra might be this way. The Yakov algebra is actually isomorphic to this guy in the finite dimensional case. So in particular, this gives us tau V irreducible representation of this. And now Lusztig conjecture says that it actually, so not Lusztig conjecture, Lusztig theorem. Theorem of Lusztig. Let G be GLN. Then character of V, it's equal to, let me write down and then I will explain what do I mean. Okay, first of all, it's equality in the class functions. No, this is just character. S is the Springer sheaf, Grothendieck Springer sheaf, sorry. If push forward, let me somehow. I will say actually more precise assertion in a second. What is important here? It's known that endomorphism of S is actually N. No, it's W. In this case, in particular, and S tau, it's just you take a tau tensor product. What's the W of S? Okay, this just is a typical component. It's tau is a typical component, so it's another G. And what is this guy? This is corresponding function. And explicitly, let me just do explicitly because this will be what this actually says. Actually says it's very simple. I think. Equivalently, it says that for every element G of Q, trace of GV, it's equal to trace of Frobenius of what? Of what? Let me write. Of what? Of tau V U bar W H R gamma. I will write this instead of R gamma if you don't mind. Something like this. Full G. What is full G? First of all, flex is G mod B. Flag variety. Of course, on this flag variety there is an action of G. So flag G is a fixed point. or it's the same Springer fiber. It is the same x to inflex g of x equals x, which is Springer fiber. Then it is known that on so this is R gamma, namely the complex of its cohomologies. And then on this guy, it's acting the affine, the wild group, so a symmetric group in this case, because we are in the GLN. And so we consider this as the typical component and take trace Frobenius. Yes. By the way, pay attention to that, of course, both sides has sense in for a general group, not necessary for GLN. Both of them are defined, but in general, they're not equal. If you want, this is because if you somehow study representations of group over the finite fields, that there are some non-trivial unipotent representations for group other than for GLN. For GLN, all the unipotent are principal series. This is the reason. In general, you have a non-trivial linear combination, which is explicit, but I definitely don't want to talk about.
So if G was a regular unipotent element, the Springer fiber is just a point. So I guess this trace will be either 0 or 1. Is that right?
Yes.
Yes. Yes. Okay, good. So questions so far? Okay. So our main result is actually that so Lusztig conjecture, which actually we were able to prove, is actually to extend this result to the Piaget case. Okay, so what our result says. Okay, let me just, yes. Oh, maybe I even can save me of writing 2 lines. Yes, actually, no. In our case, G will be GLN. Actually, G will be. Yes, what I want. You know, first. No, first, you know what? Sorry. Let us G be first. Let us. It will be unramified connected productive group. Because the construction works in general, but the equality will be true only for GLN, like in this case. Okay. Yes, and then we have I into G of F is Hori. It's again where it is before we have a barrel. Now instead of barrel, we consider Ivahori subgroup. Now, so let V be irreducible, smooth representation of G of F. Maybe I will emphasize that we with coefficient, because the smooth is actually does not matter which coefficients, but we take coefficients Q L bar because to connect it to geometry, because for geometry Q L bar, of course, would be essential, such that the same assumption is here, namely we have a okay. This means that so V gives rise to Pi, it's irreducible representation of Yakov algebra. And this is, by the way, for here probably not everybody thinks about Piaget groups, but this is precisely the same Yakov algebra that probably all the people here think about. So usual affine Yakov algebra.
You just clarify, you still want F to be function field, or you want it to be static?
It doesn't matter, both of them. Let us say, okay, it's so far it works in both settings. So far it was working both settings. At some point, when we speak about affine Springer fiber, it's up to what is your point of view? Because nowadays there is a notion of affine Grassmannian and mixed characteristic. In particular, you can do even affine Springer fiber, so everything works in the mixed characteristic as well. But let me.
Our papers don't.
Yes, our paper don't bid, but it doesn't matter. Our paper is not written, so. So yes. So anyway, now what is important fact that somehow you can ask what before we use the following fact that actually Hecke algebra was actually isomorphic to the group algebra of the Y group. Here it's not the case, but nevertheless, what is true that actually that the okay, what is true that actually if you take the affine Hecke algebra and you specify Q goes to go to 1, it's something where Q is a parameter, then you precisely get which is extended affine Y group. In particular, what I claim that actually that VI actually gives rise to representation tau of V, which is a representation of whatever U is. And you might ask, it is not unique, it's true, but there are two answers. First of all, there is a canonical specialization due to Kazan and Lusztig, they actually from their work. And actually, what is more important, that actually the class of TV in the Grotany group is well defined. And for the formula I'm going to write down, this is the only thing which matters. Yes, the only thing it's yes, actually you remember here it was reducible. Here I'm not claiming it is reducible because it doesn't have to be the case. So if you start from irreducible represents here, you don't have here. But anyway, but what is important, maybe I want to emphasize this finite dimension representation, which is important. Good. So what we did so far? So we started, let us somehow repeat. We started from irreducible smooth representation of the Piaget group, such that which has I invariant vector. It gives you representation of the Hecke algebra. Then it gives you representation of affine Y group unique into the K group. And now, and the assertion says that actually that we have this equality, except you have to do more things. Of course, here it will be affine Springer fiber, and G has to be also only compact. You remember I told that somehow it's on for various reasons. For example, the affine Springer fiber defined only for compact elements. After that, there's no. I think okay. So main result. Let me just formulate the result and then to explain the terms. Which says that and is it precisely a slight version of Lusztig conjectures, which is the following that for every V as before, and for every G of F, which is regular, semi-simple, and compact, then let us write down formula, and then it will be trace of Frobenius of what? Of tau V, tensor UL W tilde. Yes, here I want to emphasize that the tensor product has to be derived, because it was before it was finite group. In particular, the co-invariance, because we had characteristic 0, was an exact factor. So it was easy. Here it's delicate, and here it is where. Let me explain. So I want to explain what is written here, and also why the right-hand side makes sense. So the left-hand side may make sense because it's known that for every smooth reducible representation, its character is actually represented by function on a regular semi-simple element. So this is actually a number. Yes, first of all, we have a affine flag variety. which is, I don't know, LG over I, which is affine variety. Yes, and maybe I want to define recall to those who are not familiar with this guy. This is what is called. So it is a limit. It is somehow co-limit of somehow flex less than equal than I. Let us say, where this guy is projective algebraic variety, and embedding is closed embedding. So it's not an algebraic variety, but it's not very far from being mean because it is just inductive limit of projective varieties. So it's almost it's not finite dimensional object. So this is this guy. Of course, on this guy again. Yes, maybe I want to say that somehow what is its let us say in our case, what is its FQ points? It's just G of f modulo I. So I will identify I with a set of its points. So yes, where what is loop group? Loop group is yes, actually Alexis described it in his talk. It's whatever. It's its group object in the schemes such that its FQ points is G of f. Okay, so this is this guy. So this I define it this. Now the next thing is what is full G? It is the same as full G. This is the same formula, so fixed points. It is what is called affine Springer fiber.
Wait, did you say that G is GLN here?
I should. Thank you. Thank you. Thank you very much. Yes. Otherwise, of course, both sides are defined, but they are not equal. Thank you. Yes, it is affine Springer fiber. So it is what? In particular, this guy is of course closed in here. So it's a priori. It is again in projective scheme, but as explained in by Kazdan and Lusztig, that if G is G regular semi-simple, from this follows that actually it's this guy is actually a scheme of finite dimension, or say finite dimension, or with finite dimension, but with infinitely many irreducible components.
Not necessarily fine.
Okay.
Sometimes.
Yes. For example, I don't know how people are familiar, but it would be. So this is a nice example where this one P1s which are obtained on this. So it is, you know, it's a little bit infinite dimensional, but it's not very badly infinite dimensional thing. So it's almost algebraic varieties up to something. Okay, good. So at least I define it. So actually, because I want homology, because somehow homology is better defined for the. Before it was doesn't matter because it's, but here it's important. Let me just continue. Okay. Yes, maybe I want to say what is the. Yes, and now what is it for every int scheme? If you have any scheme X, its co-limit of X less than equal than I, we can define what is HI of X, which is just SJ co-limit of HJ. Yes, we are using the fact that homology is covariant, because otherwise you would like to have you know, int something int object, object of int finite dimensional vector spaces within vector space. Otherwise, we'd have pro vector space, which also fine. Some people consider, but it's more complicated object to work with. Yes, and also you can do, of course, in the derived category. You can do it's the same as complexes, because as you know, complexes behave very nicely with respect to filter limits. Good. Yes, and now there is a fact. There is a theory. Okay, there is a fact. One says that W tilde acts on the homology of this guy, which is due to Lusztig. And the second part is that actually, at least each cohomology is finitely generated in your model. And here there are two proofs. Proof one, it actually follows from result theorem of Jevayun. And proof two, hopefully, yes, and maybe the small disadvantage of this, that the proof is global. Namely, it uses Hitch invasions. It's very nice paper. I really like it, but the only disadvantage is global. So it's, and proof two, which hopefully I will have time to at least sketch. Yes, actually, I will have time at least sketch another approach that's somehow local. Local, say, sketch. In some sense, somehow I'm not only want to say, I want to just to show that it's, I want to show that complex is actually isomorphic to some explicit perfect complex. Namely, will be some stabilization result, and I will say it later. Okay, good. Now, what we know so far? We know so far. So this is complex. So it is what? It is bounded complex of finitely generated W tilde models. In particular, if you take a derived tensor product with something finite dimensional, then you know, because it's a affine Weyl group, it's essentially z to the power r, right, up to something finite. So this is so two implies that the right-hand side it is actually finite dimensional. So it is actually finite, somehow complex of finite dimensional vector spaces. In particular, trace of Frobenius is defined. Trace of Frobenius makes sense. So this is the problem with this affine story, that somehow the object we have to deal with are infinite dimensional. In particular, the cohomology is also infinite dimensional. Particularly when you want to take some trace of Frobenius, you have to make sure everything is defined. Yes, and here, as I said, somehow the main point is this result, which is due to Jevayun. Good. Okay, I guess it's okay. Now you can ask, okay, you remember somehow here I formulated, gave a two formulation, and here, so first in this form and also in this form. Now I define it in this form, and now I want to say that actually there is a theorem, theorem 2. If I have time, I will explain. If not, actually. Actually, we have a stronger result. Theorem 2, which says that actually is the same thing as before, which says that G compact, which is equal to, okay, which I want to say, now V, where this guy is D of LG. What Alex is denoted by some C. Actually, I don't know which. I don't know how to write it. some funny version of C that Tech knows how to do. I don't. Yes. Yes. This is affine Grothendieck Springer sheaf. And in order, you can say this is corresponding, this is equality of what? This equality of generalized functions. In particular, you want to say somehow what kind of object this guy is. So this is again, maybe I want to say this again equipped with an action of the affine Weyl group, and you consider the same is a typical component, and you have to say that there is some finite assertion to make sure that this is somehow makes sense. So need some finite assumption. Okay, I hope at least to formulate what kind of assumption you need, but let me do it. Okay, so anyway, somehow this is at least what you should think about this formula. Except, of course, you have to make sense what is written here, or more explicitly that for every regular semi-simple element, it's. Of course, somebody might say that in principle, you know, that for representations of PID groups, there is all the representation are locally L1. In particular, they determined by the restriction for regular semi-simple elements. This is true, but almost. Namely, it's true in characteristic 0, and we in characteristic P. In characteristic P, by some logic, you know it by some very big thing. It's one thing, and another thing. It's only true on this side. And here it's also needed somehow. I have some ideas how to make it true, but it definitely was not done.
So just so the point is that the difference between the two formulations is that here you're talking about distribution.
Yes. So here not only regular semi-simple elements that take it in account. So this result is a priori stronger, and at least up to now it's really stronger. Namely, I don't know formal way to deducing it. Okay, good. Let's now say about finite assertion. Okay, so what I want to explain, roughly speaking, yes. Ooh. Okay. Yes, we were made two results. One, for example, this one, another one, theorem of Lusztig. And now we are starting.
If you take a point which is not in this regular semi-simple locus,
Yes.
so this right, left, and right is not making.
Yes. For example, this is yes. In this case, this is not finitely generated. For example, take the trivial element, right? Take for example G equal 1. Then what is the Springer fiber? It's a affine plug variety. Of course, it's very easy, but it has infinitely many cohomologies. This cohomology goes to infinity. And the action, of course, is not very interesting because the action will be trivial on each cohomology.
No,
What? No, if you have affine, okay, if you have affine, or maybe not trivial, but almost trivial. No, anyway, it preserves every degree. It preserves every degree. In particular, this is somehow something has infinitely many cohomological degrees. In particular, this does not make sense. It's okay. It doesn't have to be, because if you think about what you think about distribution, you cannot evaluate if you have, for example, a representation of PID groups, you cannot evaluate them at the 1, because if you evaluate it at 1, you get a dimension of representation which is usually infinite. So it is compatible.
Can you explain in more concrete terms what is the content of this?
Yes, I will. Okay, I will. Let us first say this. If not, I will either try to hear. If not, during the question session. Okay, let's do it. First, I want to say in a second. Okay, let me just. I want finiteness. Okay, now finiteness properties. Let us, for simplicity, let us assume that G is G semi-simple simply connected. Namely, I don't want to deal with the center. In the case, okay, in this case, flag variety has, as I said, it is in scheme, and I say it's written in this form. Actually, there is a better way of writing it. It is co-limit of where W is W fine in this case, right? It is just the co-limit of its Schubert varieties. In particular, for example, for G, it's co-limit of G. Okay, now I want to say the following for every parachoric subgroup P in I, or standard parachoric, if you wish. Let us say WP. W is the corresponding Weil group. If you wish P, it's P corresponding to some J, where J is a subset of affine simple affines, and this is just S and J. This is generated by this guy. Okay, and in particular, what we want WP. WP is longest element. Okay, and now what I want to say is the following: there is one ingredient important, which is called. I mean, I can not use it. There is a de Mazura product for every W1, W2 in W. There exists unique element. This guy, such that element is less than or equal than this guy. It is a product. It is some very easy construction. For example, if one of them is a simple reflection, then the product is either, if it is the de Mazura product is either the product if it is larger or the opposite one it was before. And now what is important is before. Yes, and now theorem says, okay, I can either write theorem or let me do it differently. Okay, there is a natural, yes, there is a, yes, so it was about A, B, C, G. There is a natural fact. There is a natural fact that W is actually co-limit in the category of group, in somehow groups, in the whatever groups. By co-limit, I mean homotopy limit of WP of P. Whatever it means, to those who know, to those I'm sorry, this. And from this, there is a very important property for every representation V. Oh, V is given, I don't know, what is the letter W also, and X representation on W. There is a natural equivalence X is isomorphic to co-limit over P. All the co-limits are homotopic, okay? Co-limit of the following thing, you can take induction of the WP, W tilde of X, or if you wish, of the restriction. I am not writing down the restriction. And why it is true? This is true because it's it's a general fact about
Ordinary co-limit, isn't it? It's a co-limit.
it's true, it's ordinary limit, but it's also homotopy limit. Yes, no, okay. So far it's okay, but in a second we will work with complexes where it will be important. No, because of course the difference between ordinary and homotopy is so ordinary limit obtained from the homotopy limit by taking pi zero. If you have an equivalence of homotopics, if two topological spaces are homotopy equivalents, they have isomorphic pi zero, but not vice versa. This is what the usual co-limit is. No. What?
Some kind of complex.
Yes. For example, one of some complex construct. No, it's easy fact. It's easy fact. Another proof you can use it using combinatorics of affine Weil group, which of course in the end is also equivalent to this. It's easy fact anyway. Now you can ask us the following. Okay, this is to the following. For if in particular, if you have a cohomology of affine Weil group, it is co-limit. You know what? If I have time, I will explain later. Let me not explain now. Induction of WP WT tilde G. Now you know this one. This one is also as a co-limit, right? Now there is another fact which I forgot to explain. I introduced this element. Yes, there is a easy fact which says the following fact that actually for every W, if you consider cohomology of full G less than equal W WP on this, so on this guy there is an action of affine Weil group. This truncated affine affine Springer fiber of X does not take the whole affine Weil group, but because of this guy, it's what is X, it's X WP. And then I claim you can write as the following: it's co-limit of so it's co-limit of a P, and here I have co-limit of a W. Induction WP W of WP. No, so far nothing happened because I just say that somehow these guys are cofinal in all of them. Now what I'm doing the, I think I'm reversing these limits. By the way, this is finite co-limit and this filtered limit. And if so, those I don't know, people who of course familiar with the homotopic limits understand the difference, but they behave completely differently. And this, of course, you replace. So it is co-limit of the W, co-limit of P of what is written here. Okay, induction of WP W. Okay, let me just. Okay. So I wrote this guy. Let us first of all, this guy I will give a notation. I will go with notation. For me, V will be less than or equal to W, and you can ask, what is this guy? And the answer is as follows. This is what this we says it was finite dimensional algebraic variety because it's somehow it was just Schubert cell. So its homology is what? It's the whatever perfect complex of finite dimensional vector spaces. When you, in particular, it is perfect model with respect to representation of finite group. What happens when you induce? So it will be this guy is, I claim it is lies in a D perfect of UL bar W tilde, and its finite limit, it preserves this property. So what we did by using this manipulation, which is might be strange when you see it for the first time, but after that you realize that actually it's very natural. I wrote our complex. Which one? You're interested in as a filtered limits of a perfect double tilde models. And now, of course, you can ask the following. Somehow, usually, what is the main reason? You know that this is the you want that this is in the end is perfect. In this filtered limits, it's actually if and only if. Essentially, it is stabilizes. And actually, our result. What I did was oh, yeah. So main finiteness results actually says that. Without theorem says that for every G there exists W such that this colimit stabilizes, namely for every W prime less than W And if you know this, this means that okay, maybe I will say WG. It depends on the it depends on the element, namely it depends on the ramification. It's a regular semi-simple element, there is a discriminant. And it only depends how close it is to the identity. I don't want to write a formula, but anyway, it is this. In particular, what from this follows that, of course, that full guy, it is the same is this finishes this, and maybe I have another 1 minute, and I will answer to Jivay's question. Yes. And you asking the following question. Suppose you have a certain element F, and you have a D LG of LG, where D you mean this is what inconstructible. And you want to say that you want to say is called categorical distribution. I don't know whether it's true, whether it's good pure term or not. Namely, its finiteness property is certain. If it satisfies the following property, for every congruent subgroup Kn in LG, and for every subscheme or quasi-compact subscheme quasi-compact subset something. No, in this case it's LG. But let me write it in this form. We have that if you have F, if you convolve with this, and after that you restrict to this, it belongs to the D constructible. If you remember, somehow before we only restrict us to fiber. The idea is, of course, okay, if you wish, convolve with star and restrict with shrink in our notation, but of course, if you wish, this is this. And maybe I want to say that somehow what is important, you can ask what is the relation between this and the previous one. The idea is if you take a regular semi-simple elements, that if you have an n sufficiently large, greater than which n depends on the discriminant, that the convolution does not change the fiber at this point. In particular, if you know this, that somehow that when you pass to the fibers at the regular semi-simple elements, it doesn't change. And this is the reason that the cohomologies of fibers are finite dimensional. But as was questioned, if you take a G equal 1, it is definitely not true. So this is actually operation, non-trivial operation. In particular, the fiber at 1 will be infinite dimensional, but after you averaging, it might be finite dimensional. Thank you very much.
Any questions?
So I just quick comment in the interest of full disclosure. So I think you said several times that we prove Lusztig conjectures. I mean, this is, I'm not sure it's accurate because
Yes,
it proves something inspired by his conjecture.
Yes,
like,
yes. Lusztig did different. The difference is that we consider derived somehow when we consider isotypical component, we consider derived isotypical component, and Lusztig doesn't.
think it's a better kind of.
Yes. But nevertheless, we try to understand Lusztig conjecture and translate to the form we could understand. And
another quick question. So here, this S tilde tau V. So Alex talked about the